Welcome you all for the 15th session. So what I plan to do in this lecture is to show you a real implementation from Intel, a processor which is a very high-end processor. All of you might have heard of Core i7. I want to show you the architectural diagram of this core and then tell you what all you know already to understand those details. So in fact, you are in a position now, provided you have followed all the lectures, even if it is partially you have understood, you can still read up about these latest architectures which are in the market now. You can take up some document, read about them. You may not understand 100%, but I am sure at least 70 to 80% you should be able to follow from what you have learned so far. So let us now go into the details. I am going to introduce some new terms. Simultaneous multithreading. You have heard about one acronym similar to this, which is SMT. That is synchronous multiprocessing, where multiple processes are running on different cores and they all have the same kind of access to the memory. Symmetric multiprocessing. I have explained it way back before the test. So don't get confused with the SMP and SMT. SMP is symmetric multiprocessing, where multiple processes run on multiple cores and they see the memory the same way that every process running on those cores see. That's why it's called symmetric multiprocessor. It's from the software perspective. When you have processes running on multiple cores, how do they see the memory and how do they interact with the memory? In SMP, the structure is like that, the architectural structure, that each process have equal, what do you say, let me rephrase it. All the processes, they see the memory the same way as others. And everyone has the equal access to those memory and their delay in accessing that memory is same, uniform memory access. SMT is a hardware feature. It is simultaneous multiple threads running on a single core. So those who have attended the systems programming, they know a little bit more about processes and threads from the implementation perspective, especially from Linux perspective. Even those who have not attended the systems programming know about the processes and threads. I told you earlier in the OS course, processes are individual entities. When they do a context switch, the processes need more amount of work to be done to remove one process from a CPU and bring another process into the CPU. And I told threads are part of processes. They run in the context of a process. So context switching between threads of the same process is quicker and they have access to the process files, the process memory. So they have a common access, but they run as an individual threads within the process. So that is the difference between process and threads that you know so far. Whereas system programming guys know, Linux implements processes and threads in a similar way. They provide the same data structure, which is process control block. Either it is a process or a thread, they allot one PCB to them. But behavior wise, they have the similar thing, like threads inside a process. So they have access to the process memory, whereas two different processes cannot access the memory of each other. So they are totally separated and they do not even know the other processes exist unless they communicate with each other through shared memory or any message queue or semaphores. They do not even know the existence of other processes. So this is the context about process and threads before we get into the details of how threads are implemented in a CPU. So I am going to take a Intel's technology which is called hyper-threading, and I am going to take up Intel's design Core i7. The name given to that design is Nehalem. Nehalem is a city in the US. They identify every processor new architectural design with some name. So they come up with some new names. Every company has this habit of giving a name for that family of processors, and then this is the name given to the chip which is coming out with some particular features. So you may find different processors, core 7, core i7 or core i6, whatever, following the Nehalem architecture. So Nehalem architecture is like a superset, and individual processors designed and released to the market by the company may be different. They have a different number of cores in them, maybe the amount of cache in them will be different. So they all change, but they all follow the same Nehalem architecture, means they follow the same philosophy, the same architectural features in implementing them. So you must be aware now that we are not going to talk anything lower than superscalar processors. So this processor is a superscalar processor. That means it has got multiple functional units in them and the instructions can be executed simultaneously. Whether they implement scoreboarding, no, scoreboarding won't be implemented because it has got a lot of limitation. Whether Thomas-Solo's algorithm may not be, maybe better than that, but they do some implementation of dynamic instruction scheduling. They have multiple functional units in them and they do it. Most of these details may not be released out for common citizen like us. If you are part of Intel, maybe you will come to know more details about that. But being a consumer or even a designer or a OS developer, you are given a limited amount of information, not everything that they do inside. Then they will lose their intellectual property. So my aim is to complete this before the break and then teach you two more concepts at a very high level without going into the implementation, so that you know what they are. And most probably we may have to do a self-study of this particular topic because it is very simple. Okay, now let us see where we are. We were talking about functional parallel architecture. I hope you know out of this how much you have already been taught or you are supposed to know. I'm sure you know. These three are done. Now I am going to talk about thread level parallel architecture. Do not assume if I am talking about this, anything that you learn here or anything that you have learned here or even anything that you have learned here will not be part of it. It is inclusive of all that. In fact, all of them are there. And on top of this, whatever you learned, they are going to add something more. So I am going forward by addressing each of them separately, and I am going to talk about something individually about threads, and then I will talk about Nehalem or Core i7, which has got all the features of whatever you know so far. Whatever you know so far and what you don't know so far also. Okay, and what you are going to learn today will also be there. Okay, simultaneous multithreading, SMT. Hyperthreading is a name given to this feature of having multiple threads in a processor by Intel. It is its own name. Nobody can use this. It's a Intel's proprietary. They are given the name for this. Now, let us see evolution. What all you know? Simple pipeline we saw. MIPS pipeline, which is similar to this, exactly same. So when I say memory hierarchy, always assume it includes, except the processor, all that you have seen below in the memory hierarchy. Cache level 1, level 2, level 3, main memory, everything falls under this. It is all captured in one single box. We are only worried about this portion of this architecture. And this can be implemented in any way. It could be single unified level 1 cache or separate level 1 data cache and instruction cache followed by a unified L2 cache, or separate instruction cache and data cache at the L2 level also, then unified L3 cache. It can be anything. One thing you remember, if I am talking about cache and then I am saying L1, L2, L3, assume if there is a cache, whether it is this or this or this, they will be inside the same chip. You cannot have a cache outside the chip. Then it doesn't serve the purpose. Cache is there for accessing the contents at a faster rate. It cannot be outside the chip, because once something is outside the chip, it involves delay in terms of the distance, in terms of accessing the memory, the time taken to give the signal out and get the data back increases. So only main memory will be outside the chip. Don't assume that main memory also inside the chip. No, main memory is always outside the chip. It will be on the motherboard and the chip will be accessing it from outside. From inside it will be accessing the main memory, which is outside the chip. Whereas all the cache, either whether a processor supports L1 or L2 or L3, they will be inside the chip. One more thing, you cannot have L3 cache without L2 and L1. Similarly, L2 cache without L1. Of course, this is very implicit. Okay. And one more thing, size also will be like this. This size will be lower than this. This will be size. And one more thing, unified. Suppose if I say L2 is unified, I cannot have L3 as a separate instruction and data cache. Unified, once it starts off, it has to continue. Okay, I can have separate data cache and instruction cache here, separate instruction cache and data cache here, and unified cache here, no problem. But if I say this is unified cache, I cannot have a separate instruction and data cache further down the memory hierarchy. So these are all implicit thing which nobody tells, but it is it is to be understood. Okay, now let me come back here. This is the context. If I say register, set, and PC and SP together, I am showing it here to say that this is the CPU context. When I say a process is getting switched, context switched, what is saved is the content of all of them. When I say I am saving the content in SP, it is only a register, stack pointer register, and its address. Do not misread that I am saving the whole stack content. No. Stack content, where is it in the memory? It is in the main memory. Somewhere you have identified as a stack, which is residing here. This is a stack pointer of this particular process pointing at that location. I am preserving this value. And remember, these are all logical addresses, virtual memory addresses, not the physical memory addresses. The memory management unit comes in between. Okay. All these things you have to know. Now I am showing this outer line to say that these are all in a single chip. So memory hierarchy only includes cache here. Okay. It doesn't include main memory. Main memory will be outside and there will be a bus interface, address and data. Okay. Now this is a single threaded pipeline. I can have multiple threads running on this pipeline, no harm, provided I am running a OS which supports multiprocessing. I am using thread and multiprocessing in a I'm not differentiating them. If the OS supports it, then I can implement it. If the OS does not support, I cannot have a multiple processes running on a chip. We need a support of OS. And I'm sure you know the reason, which I explained it in OS course. Now, next thing, what we learned about superscalar pipeline. So these are the modules which are single unit in the chip, and multiple execution units are there in the chip, functional units or execution units. And why am I showing this dotted? Because each of those execution units may take different cycles to complete based on what is running on them, which instruction is running on them. Now, what is the issue state? It issues the instructions on them. And it also makes sure before running those instructions, there are no dependencies. All the operands are given and the execution units can start off from there executing the instruction. Now, the fact that these execution units are starting off at different point in time and they are executing different instructions, which take different number of cycles to complete, what you see coming out of these execution units are completed instructions at different point in time. So we are issuing the instruction in order, the way the instructions came in, and getting the execution completed out of order. Now we need to make sure that the program order is maintained, the consistency is there, correctness is assured. We need to make sure. That means what? We have to give a outside view. The programmer should think that these instructions were executed in the same sequence it was given to the CPU. Understand? See, the programmer or the application which is running assumes the instructions were executed in the same sequence. It doesn't know CPU did something inside. For that to be true, CPU should take care of it. It is like this. When your parents are out, you are at the home, your sisters and brothers, what do you do when parents are there, not there? There will be a total chaos in the house. Things will be spread over, books will be all over on the floor. You may be watching some different channels. Now, calling bell comes. One of them is coming in. What do you do? Rearrange everything. Look as if there is a book on your lap. TV will be off. Things will be clean, and one person will go and open the door. So you want to give a similar effect that this is what was happening in the house with the absence of parents. You and me did the same thing. Okay, don't worry. So CPU does the same thing. It does all kinds of things to do here its intent is to do good for this programmer, and then it takes care that while writing back it writes all the results properly, that this guy does not even know so many things happened. So this is superscalar. And I talked about ROB, reorder buffer, which takes care of this writing back the result in a proper sequence. So I hope this is clear. I am giving actually a revision of what I covered so far. Okay. I am not going to spend some time revising it. This is the revision. So single threaded superscalar pipeline. What I mean by that, one single process is running during this time, one process. That means there is only one context. Whatever is happening here all belong to this context. Okay. So if I need to schedule another process in the superscalar, what should I do? I should save this context, and so many instructions are there here which are halfway through. Flush them all, scrap them, kill them, bring a new process into the system. I don't try to do something to come and take the results out of this or copy all of them so that I can start off from there. No. Here also the same thing. So many instructions may be in the different stages. It doesn't care. That all those things are forgotten. It will be again started off next. Don't think that it will not be run. It will be run again, starting from where it left off. So this is the place which is having the information about what is done completely. What is here shows that what are the instructions have been executed completely. Suppose I have set of instructions. Okay, it has been completed till then. The register set matches with this value, whereas all the instructions down the line are all here, either here or here. Okay, now you need to do a context switch. OS says that no, I am going to stop this process. I want to switch context. Then OS will not bother about this. It will say whatever has been done so far and then start off from there where it left off. So this will be executed later on during the next scheduling of the same process. So it will go through the same pipeline again. It may be doing the same job it did prior to the context switch, but doesn't matter because the instruction execution is much faster rate than the frequency of context switch. So it is not major difference or a major performance difficulty or performance loss for repeating these instructions. No problem. Okay, because if you remember, context switch are happening in terms of milliseconds and the instructions are being executed in nanoseconds. So remember, gigahertz is the frequency of the clock. Every instruction takes nanoseconds of execution time, and you can imagine the scaling. You have to imagine the amount of scaling between what you do, how frequently the context switch happen, and how fast the instructions are getting executed. You should have that idea. You are no longer a fresh engineer. You are you know everything. Okay, you are in the final year now. Okay, now I am going to introduce another word: single chip multiprocessors. What I mean by that, I have a single chip which has got a multiple cores in them. Our own laptop has a chip which has got multiple cores. What I mean by multiple core, each of them are individual CPUs. Each of them are individual CPUs. That means what? I can run one process here, I can run another process here, some other process here. No harm. And OS knows about it. In fact, OS knows this process P1 is running on which CPU ID. The processor gives a unique ID for each of those CPUs. ID1, ID2, ID3. So OS knows pretty well how many cores are there and if it is scheduling a process, on which core a process is running. How does it know? Because the processor is giving access to that values. So there are some instructions to read the CPU ID of the core, which are accessible only to the OS, not to you and me. As a user, I will not know on which processor my process is running because you are at the user level, you don't have access to the core level details. Whereas OS is running at the kernel level. Some part of the code is running at the kernel level. So it has got the special permission to, in the kernel mode, to execute those instructions to know which core I am scheduling a process. So where is it stored? Suppose when it is context switching, it will store the CPU ID also along with the PCB, the process control block. It will store that so that it knows if suppose on process is context switched, it knows that this process earlier was running on some particular core. So next time when it is scheduling it, it might decide to put it on the same core or different core. It depends on some algorithms. Okay, I will not go into the details of them, but it knows on which core which process is running. That means you have to have a separate register set for each of the cores. And similarly, you have a PC and SP. Okay, because each of them are running different processes. Okay, what about memory? What about cache? Cache is same. Cache is same sometimes, or it may be individual for some other implementation. So let me explain. You have to know the details of the processor to know whether the L1 cache is separate for each of the cores or not. Similarly, L2 also may be separate for each core. You have to know from the processor specification. And L3 cache, some cache will be maybe common to them. So depending on the implementation, the cache, the higher level, which are very close to the CPU, may be individually given to the core, or it may be common across all the cores. So in this picture, I am showing it to you as a memory hierarchy is common. That means I am assuming L1, L2 are not unique. Otherwise, I should have shown L1 here, and then L2 is common. I have to show. So read the picture and get the information. What is it showing you? Here it is showing you there is an individual memory there. That means don't think that it's a main memory. Main memory is outside. Individual memory means indirectly it means it is a cache, which is separate for each core. Okay. So what is it? This is a single chip multiprocessor. That means it has got multiple processors inside a single chip. And memory hierarchy, what is shown here is actually I am showing it here, but maybe you have to take it with a pinch of salt. Individually L1, L2 are shown. Okay, don't worry. I want you to understand the higher level concept. Okay, fine. Now I am going into the simultaneous multi-threading, SMT. Let me explain now. Is this picture same as the previous one I showed you? If you are alert, you might have seen what is the difference. Let me show you again the previous picture. Here also there are superscalar pipelines. Here also there are separate context. I will call them as context because it includes flags, PC, SP, interrupt controller, a lot many things are there. Not only this. These are all very minimum only shown. Okay. So each of those cores have this common, separate, and they have a separate control unit for the superscalar pipeline. That means what? The instructions of a particular process running on this core has a complete control of what is running on all the execution units. In other words, all the functional units in the superscalar pipeline execute the instructions belonging to a single process, because there is only one context and one pipeline. There is a one-to-one mapping. That means OS, when it is scheduling a process, it has the process has a complete control of the entire superscalar pipeline. When I say the entire superscalar pipeline, it also includes all the execution units in the pipeline. So what do I gain or lose? Let me talk about it. I send a process. I schedule a process. I means OS. It is running on the superscalar pipeline. Now different instructions are issued belonging to the same process, and we saw the div, load, store, add, all that. There were so many dependencies, and then we saw these functional units were not effectively utilized. Most of the time, something is to be coming from other instruction, and the functional units were waiting for those instructions to complete or provide the data, so that data hazards don't happen. What are we losing now? We are losing the performance because we are not able to make use of all the functional units. What I mean by make use of, I am not able to schedule instructions on all the functional units which are there at all the time. I am not able to schedule instructions on all the functional units all the time because there is a data hazard. I need to wait for some results to come from other. Because of that, some of the cores are just idling. They are there in the core, not doing anything useful. Can I do something within the same process? No, because the instructions have been decided by the programmer or by the compiler based on the program. This is the data dependencies in the program. I cannot tell user, write such a program where there is no dependency at all so that I can run your program efficiently. I want to keep my functional units occupied. Please give me such instruction. I cannot tell. I have to live with this. Now what do? I should think something. That is what Intel thought. And then use those free slots for some other process. Understand? Some other process within the same core, within the same superscalar pipeline. This is little difficult to comprehend. Let me explain. If I am given one stream of instruction belonging to a process, I am restricted by the data dependency and memory access. Suppose I have a load store instruction. The data is not in the cache. I'm not going to get the data immediately. So it is going to block. So there are so many such things are happening. Even instructions may not be there. Instruction memory is, cache is, there is a hit, there is a miss. So if I am having a single process, I may not have sufficiently large number of instructions to schedule on the functional units I have. Whereas I am given a freedom and I am given another stream of instructions along with this stream. I am having now two things. I can eat much faster now. In the sense, I can consume more instruction now. If one is not giving me because one is blocked because of data dependency, I will look at the other guy and then, hey, do you have any similar instructions which I can schedule? I'll put it. So if I have this flexibility, I can keep my functional units as much as possible busy. So this is the thought process behind SMT. Now, if you see the difference, this control unit is same. Whereas they are all separate individual context. Now, I can schedule them, any of them into any superscalar pipeline in this context. Okay. Here I am showing you this particular example shows you that I have multiple superscalar pipeline where I can take the instruction stream of any processes and then scheduling them on this superscalar pipeline because there is a common control unit. Okay. So in this picture, suppose this dotted is not there. Okay. Assume that only there are three. How many processes are running? There are only three processes. And you have multiple scalar pipelines shown. I will show you a real Intel implementation wherein you will see that there is only one core, one superscalar pipeline with multiple context. This is a generic picture. Understand this. I have a control unit which will schedule these instructions, whether it is belonging to a process P1 or P2 or P3 on any of those functional units which I have. I may have a single pipeline or multiple pipeline, doesn't matter. Okay. In this case, it is shown multiple pipeline. I may even have a single pipeline, but I will take streams from multiple processes so that I can schedule them if one functional unit becomes free. Then I may have a single memory management unit. Okay, this is little higher level explanation. Let me explain again. We are thinking about multi-threading because our functional units are, this is what I want you to carry in your mind. We are thinking of multi-threading because we are not able to keep the functional units busy with a single thread or a process running. So thread and process are almost synonyms here, synonyms here. So I am not able to keep the functional units busy because I have only one stream of instructions and they have a dependencies and I cannot keep them busy. If I have one more stream of instructions coming from different process and it has got a different context, because I need to have a different context. Each of the processes need to have a unique context. That means they have separate register set physically. It is all not virtual register set. Do not get confused with this and the renaming business. There are multiple R1 registers in the processor. Okay, within the same chip. Okay, and I have a different stream coming. I can schedule them. Okay. Okay. Now let me come to our friend Intel's implementation. Here it will become much more clearer. If you are not understood much, you will be doing it now. This is the RAM, main memory. I have stored different processes here. Okay. Don't worry whether it is a process or a thread. They are individual sequential execution. Okay. These different colors show different process code data stack in the main memory. Now I have a core which can take two streams simultaneously. Assume that it can take two different processes. It can take instructions to come into the CPU. See, normally I have told you many times in the OS course that only one process can run in a CPU. Only one process at a time. I told you many times. And I would have also told, assuming there are no multi-threading in that. Now, my statement is little different. Even though there is a single CPU, I am assuming single core. If it is supporting two threads in them, two threads, that means I have two contexts inside the CPU. I have a different register set and another register set. Stack pointer, PC, everything is double. You have two of them. It is like this. In your house, only you are there, single thread. Your sister or brother came, another thread. In the same CPU, both of you are able to execute, but you will be sharing the resources, right? You will be sharing the resources. What is there at home? If there is a piece of cake, maybe before this brother, you were consuming everything. Now you don't have that luxury. You have to share it with other sister. Otherwise, there will be a big fight. That will be happening anyway. So same thing is true here. You have another context, another thread in the same core. Then whatever is there in the core needs to be shared by both of them. Now, what is happening? The CPU will be fetching instructions of two processes simultaneously because it knows that the CPU has two threads. It has a capability of running two threads. So both of them will be running simultaneously. Similar to your brothers and sister, you will be in engineering college, your sister will be in the school. These processes may be in different stages of execution. They are, as far as interrelationship goes, they are independent. What they do are different. You are studying BE, your sister may be studying something else, but both of you are sharing the same resources in the house. Same way, these threads are sharing the same resources. What I mean by resources inside the CPU, it is nothing but functional units. It's like bathroom in the house. If one thread is there in the bathroom, you cannot enter. So same way, here one functional unit is occupied by, suppose there is only one divider and another thread is running its execution, its instruction, divide instruction on the functional unit, then the other thread has to wait if there is only one functional unit. So they share, but they are independent of each other. When they will give a div instruction, you don't know. So that is the advantage from the CPU or OS perspective, that I can make use of the functional units efficiently if I have multiple threads in them. So if I show the same thing here, what I'm showing here is thread X, thread Y, and white means unused. So I am getting two streams. Don't think that if some there are white is there, white means unused. A functional unit is not working, not busy. I cannot schedule another thread because it is limited by number of context you have, number of register set you have. You cannot schedule more than the number of register set in the system. So maximum two, I can parallelize among them, and they are pretty independent. That in the sense, OS can remove one process from one thread. It can context switch and then bring another one while the other one is continue to run. Context switch can happen for one thread while another thread is continuously running. So these are all some things which you have to understand how it is happening inside. So let me explain now in another picture. Both of them are coming in. Instructions belonging to both threads are coming in. In a single core system, it will all go. Let me explain. Hyperthreading technology. Throughput is okay. Here what is shown is logical processor. Okay, let me explain what is the physical and logical process. Here I have only one context. That means I cannot have both of them simultaneously together. Understand? This is single context. This is a register set. I call that as a logical processor. Physical processor is one single core, and if I have two different register set, I call them as two logical processors. If I don't have two and I have only one, I call it as one single logical processor. Now I'm showing you both to make you understand. This is only one logical processor is there, similar to what we have seen so far. That means I can have only thread 1 coming in first, and it is running now. Okay, and this coding is only for this picture. Okay, don't get confused. Yellow is here also and here also. Okay, I'll put a big line so that you don't get confused. Here yellow means empty, not used. Here yellow means it is empty. Maybe I will put a legend for this also, because it might confuse you. Here what is happening is different functional units are there. At different point in time, there are three resources. Okay, maybe one load, one store, one floating point adder, something like that. Then if the instructions are coming, I am able to schedule only one instruction, and the rest of it I am forced to free it. In the next cycle, I am able to schedule two instructions, one is left to free. Here I don't have any instruction to schedule, everything is waiting for something. It may be because of memory. Okay, it may be because of memory access. Okay, nothing to do with the other instruction result. You should understand. Here only one. Okay, so utilization of CPU functional units are very less. And then once this thread goes out, another thread enters, and you will see only some oranges here and yellows there. No blue and orange together. Okay, here single thread at a time. Now I am talking about multi-threading. Here I am talking about two threads. I may have 3 threads, 4 threads, but normally processors have 2 threads. It depends on the implementation. Some super computers may have multiple threads. If I have 2 threads, I can have the instructions belonging to both the threads simultaneously within the CPU. And at any point in time, one functional unit is executing an instruction belonging to this thread. Same time, an instruction belonging to this thread is also running. Remember, understand it? They are instructions belonging to different processes. Suppose let me give an example. This resource is a floating point divider. This is now executing a div instruction belonging to this thread. Whereas if this is an integer adder, it is executing an instruction belonging to this thread, an integer addition operation. And in the next cycle, it changes. The functional unit is now executing an instruction belonging to another thread compared to previous one. So you are sharing the functional units. U means the processes or threads. In this case, I'm calling them as thread because multi-threading, not multi-processing here. So from the Linux perspective, both are a process only. Let us call it as a thread now. So they belong to different threads. Instructions belonging to different threads run on each of the functional units. Okay. So this is the beauty of this. This is called hyper-threading. So we have, what is the gain? If you see, number of yellows were more here, whereas it is less here. But still you will find yellows. Yellows means not used. It is still not 100%. Don't think that you can have everything occupied. It depends on the stream of instruction you get and the dependencies with them, among them, and the delay due to memory. A lot of issues are there. So they say that this SMT hyperthreading improves the performance by another 30%, not just 100%. It's not doubling. It is not doubling. It is improving. But why did Intel do this? Because they felt that adding another register set and a control mechanism to run through different instructions is very less in terms of chip area, and they get some benefit out of it. And Intel is very advanced in terms of trying out different, any company to need to survive, they have to do it. So Intel does it. That's why it is there in the market, number one semiconductor company for the last few decades. Okay. So fine. Now Nehalem architecture, what we are going to see is a quad core. Now 4 cores are there, which each of them having capability of running 2 threads, similar to this, 2 threads, not more than 2. Okay, now you are all ready to understand it. Now let me just give you a summary. Single core means a chip having a single CPU state, interrupt logic, execution units, maybe multiple execution units may be there, but only one process is running at that time. Cache is used by, of course, there is one cache and it will be used by the process. Cache is inside the CPU. Multiprocessor. Multiprocessor means there are different CPUs. You will see 2 CPUs on the motherboard. They are not inside each other. 2 multiple processors on the motherboard. And you can build a motherboard with any processor you want. The utilizing them depends on the logic outside. They are different processors altogether. They happen to be together in a single motherboard. It doesn't mean that they are inside each other. Okay. Multi-core. So that's the difference between multiprocessor and multi-core. Multi-core means these CPUs are inside a single core. Sorry, single chip. Multiple cores are inside a chip. So here they are outside. There are 2 different chips. Here in a single chip they are there. That means they can decide whether they want to use the other resources or not. In this case, they have their own cache and it is showing that they don't share anything in the chip. Normally this is not the case, but it is shown one of this way of doing it. Now this is the normally what you see. Multiple cores, execution units, but they don't have a cache inside them. They share any cache outside. Okay. This is multi-core with a shared cache. They don't have an individual memory for each of the cores. Now another one is hyper-threading. Here you have a CPU state and the interrupt. Okay, let me tell you what I mean by interrupt logic. Each of those CPUs can be interrupted individually. I can interrupt this processor and this can continue to execute. Do not assume if I interrupt this processor, this fellow also will stop. No, they will run. Okay. It is like this. When you have a morning 9 o'clock class, you get up with the alarm clock, your sister will be sleeping. So when the interrupt comes to this core, it will wake up, but this guy can continue or do whatever it was doing. So it could be sharing the executive. If it is called hyper threading, they are sharing the execution units. That is very important. This is very, very important. And they need to share cache also. They don't have a separate cache for each of those threads. They have a only context which is common. The CPU register set and the interrupt logic is unique. Rest of it is sharing. Okay. So this is hyperthreading, which I explained just now. This is multi-core with the hyperthreading technology. There are two cores. They are inside a single chip, and each of those cores have multiple threads in them. This is what we are going to see now. Nehalem, sorry. Their quad cores are there. Here only I am showing you two cores. So core means a CPU, and inside that if they have a separate register set context, it is a thread. So each of them are having two threads. Okay. I hope this is clear. Now we started off for thread level parallelism, and thread level parallelism means multi-threading happens to be there. And I explained to you how multiple threads are there and how is it implemented in Intel, and what is hyperthreading, and how is it sharing the resources. That means two streams of instructions getting executed by superscalar processor simultaneously. So let us, my intent is not to go in detail about everything here. I want you to give you a confidence that you can now open a latest architectural specification document or any article on that and read through it. You have enough knowledge to read through it and it will make sense to you. Okay. I want you to understand that, because you have to be on your own picking up knowledge. So I picked up one and a very good document, which I'm going to share it with you. This is an outsider talking about Intel processors. And one thing I want to tell you that Intel processors have very good documentation, very wonderful documentation. I have been seeing their Intel documents right from 1987, okay, from 8086 onwards. They gave very good documentation. If you have the document, you can understand everything about the processor. That's the beauty. Maybe I don't need to record it, but what I have observed in ARM documentation is it's not as thorough as what I see in Intel. There are some, I have seen some mistakes in the document, and some of you who have done some self-study with me on ARM core, you might have realized it. It's not that easy to understand some of those explained, because it is spread all over the place. Nobody talks about the architecture in one place coherently. You have to search around and then make sense out of it. Whereas Intel, documentation is good, as well as supporting things about the architecture is also good. Right? Actually, this document is one thing which details about what is done inside the Intel processor. So let us see. We'll go into that. It was released in 2008. Okay, it's still not the recent, 12 years old, but these are all there right now. Intel Core 7 is being used in servers. Let me tell you, this is a 64-bit processor. It can address up to 2 power 64 locations, physical memory, and don't have to remember everything. There are different register sets. I want to give you, how big it is. See, there are 64-bit process, register set, 16 are there. 16-bit segment registers are there. The Intel is a segmentation memory. Paging is also there. It is segmentation plus paging. Flags register, instruction pointer, and As I told you, the integer register set and floating point register set, they have 80 bit. 80 bit means what? Double. Okay, double precision. Floating point data registers, and then control registers, status registers, and there are some instruction pointer registers. This is to address those in the memory. And we also have a MMX, which is called a multimedia extension. I will not go into the details of them. It's a separate set of instructions for media processing, image processing, video processing, audio processing. And finally, XMM. XMM is a SIMD support. SIMD is what? Single instruction, multiple data. So that means what? One instruction is operating on multiple data. In that case, you need to store those multiple data somewhere, correct? And you know, any instruction to operate, to get operand, it has to get it from registers. That I have told you, risk. Always any instruction needs to get the operand from registers. Now what is the SIMD doing? It is operands need to come. There is one single instruction needs to get multiple data as an operand so that they can execute them simultaneously. So there is a very long 128 bit XMM registers which are having multiple data in them. Okay. So this is how SIMD is implemented in a processor, and this Intel processor has SIMD also inside. They have instructions which are SIMD type. There are CISC type of instruction actually coming in, floating point instruction coming in, integer instructions coming in, and multimedia instructions coming in. You can see the complexity of how many instructions, how many different types of instructions, and how many register set they operate on. Each of those instructions, based on their type, operate on different register set. It's not only single register set that you have seen so far. So I want you to understand the size of what you are going to get into. What you have studied in Arduino is like a toy car, and what you need to ride when you come out of the college and get into the car is a real fast car, racing car. So you have to map. You have been riding a toy car and you need to get adjusted to this. That's a transition you need to take. So these are the register set. These are the multiple cores. Let me, I'll take another maybe 10 minutes or 15 minutes before we break. We'll complete it. I will not go to the details, but I want you to understand how complex a real processor looks like. Okay. So there are quad core. Nehalem chip is a quad core. This CMP I told you. So there are 4 cores in them. Each of them are running at 2.8 gigahertz clock frequency, and they have a common L3 cache. See, L3 cache is also inside the chip. That means L1 and L2 are here. Each of them are having L1 and L2, individual chip memories. This is very important because tomorrow's class I am going to talk about multi-core and cache coherency. This is exactly what is done by this processor. Cache coherency between the cores, the caches inside the processor and the common cache outside. How they coherently access the cache. Okay, I'll talk about that. I have not talked about multi-core at all much, so I will finish it with that tomorrow. This will be a good introduction to you. Nehalem actually implements what I am going to talk tomorrow. And there is a integrated memory controller connected to the DRAM, which is DDR3. Okay, and they have a width of 8 bytes. So you can see number of bits. That's a width of data width. Okay, 64 bits. It can read 8 bytes at a time in single cycle. And there is some logic to interconnect to other devices, and the memory speed is this much gigabytes per second. That's all you have to know. You don't need to remember everything. Understand that. This is called uncore and this is called a core. That's all. That's a name and nomenclature. This is quick path interconnect, QPI. Quick path interconnect. Okay. Now I am giving you more details. Inside each core, what is there? I told you both L1 and L2 are inside. You can see them. L2 is a unified cache. That is, both instruction and data reside in this cache. Individual instruction and data cache at L1 level, and it has got a register file. All the registers I showed you, MMX, everything that I showed you, all of them are there. It's not some R0 to R31. Sorry, it has got hundreds of registers, hundreds, all different type of registers. It can handle different instructions, floating point, instructions, integer, MMX, SSC, you name them, all of them are inside. Then there is some queue, means this is all some data which is coming from this, or instructions coming from there are queued up and then fed to different core. Don't worry about it. It is complex as I show you. And this is L3 cache, which is also shared between the cores, but it is not inside, it is shared. These are all individual memory. Only this core has this memories. I'm not saying that only this has an access. I will talk about tomorrow how these cores can talk to each other, how they can access each other. I will talk about it tomorrow. I will defer it tomorrow. Okay. Okay. Now, what is this picture? This is the micro photograph of a chip, of a Nehalem chip. Why am I showing this? I am showing it to you to give you a idea of how much of memory, how much of size in a given chip, how much of size each of those modules take. You can see that each core is taking this much of space. Inside it, L1 cache is there, L2 cache is there, all the register sets are there, superscalar pipeline is there, functional units are there, everything is inside. Same thing is true. You can see the complexity now. And cache, just the L3 cache is taking so much of space, almost half of each core. Cache memory occupies more space. Why? It's SRAM, static RAM. Static RAM is built with multiple transistors. And because of that, the occupancy of a chip area is more. And then you see the memory controller. This is for accessing the main memory. It is occupying those spaces. Remaining IO, all the IO modules are here. So this is the relative size of each of those circuitry occupying space in a chip. Is a micro photograph of a real Nehalem chip and gives you how they have architected it. One more thing, if you see, they have kept them all together, not just because they want to put a nice border around it. It's like a plots. When you have a house, they're all lined up like that. They put them all together because the core, the CPU, functional units running on them, needs to access them which are close to each other. Then only they will be able to read them faster. So as the memory hierarchy, as I told you, the distance between the CPU and the memory goes on increasing. It is actually true physically. L1 and L2 will be closer, and then L3 will be little farther, and main memory is outside the chip. So memory hierarchy, what I explained to you, they all is exactly true. Physically, they are also at a larger distance compared to the memory which are closer to the CPU. Okay. I am giving a higher level view of the Nehalem core. This is a single core. Okay. You see, it's a single core. As I told you, it's a superscalar pipeline. That means it has got multiple execution units. Okay. I am localized to one core now. I am not even talking about L1, L2 inside them. I'm not even showing you the register set. Okay. Register set is not shown. They are there. I'm just showing you the pipeline, so superscalar pipeline. And then I'm showing you some cache also, which is instruction cache and data cache. Both are L1. I'm not showing the L2, L2 cache is also there. Okay. If you see the picture here, 1 second, L2 cache is unified, L1 cache is separate, and register set is there. I am talking about this functional units and all the pipeline, which is called as a core here. So that is about the core. L1 data cache, L1 instruction cache, L2 data cache here. Sorry, L1 data cache and L1 instruction cache, and L2 unified cache is here. It is within the core. So in a Nehalem chip, you have a 4 identical blocks of the same thing everywhere. Okay, inside a chip. Remember that. So instructions are fetched, pre-decoded, you know. Instruction queued, I told you, it is in the FIFO order. Decode, I have explained to you. Initially, pre-decoding is done to understand what type of instruction it is. Decoding is to know what are the operands have to be accessed. And then I told you about renaming yesterday. If there are data hazards which can be avoided, is processed here. This block takes care of replacing the real instruction registers with the renamed registers, which are physically located in the reservation stations. So the renaming is nothing but giving a new name to a location in the reservation station, saying that I am going to maintain the results here, not in the register set. Register set is not shown. You can assume something here, okay, which is accessed by all these units. So that is the, once renaming is done, that means what? The dependencies, whichever can be avoided, is taken care of. Then those instructions come here into the ROB. ROB gets the instructions, reorder buffer gets the instruction before the execution, because here only they get it in the sequence. So our reorder buffer needs to maintain the instructions in the order. It will know the order only at the input. If it doesn't get it during the input, it will not have it. So it is initially put inside, but execution is not done. Those instructions are not executed yet. They are kept, no, these new instructions are kept on adding into the ROB buffer. And then whenever they complete execution and the results can be written back, they are removed from the ROB. So it is like a cyclic buffer where instructions come and go before execution, and they will remain there till they complete. Now, once it is inside, I can schedule them on the reservation station, and functional units will execute them. So they will be below. They will take it from the reservation station and execute it, and they put the result back into ROB. They don't write into the register set. Remember, they put the results only in ROB, and from ROB it goes into register set. So that's the sequence. If I have to tell you the sequence, this is one. Now, what are these? If you recall, I told that Nehalem Intel or any Intel processor implements CISC type of instructions for the outside world, CISC type, and they use the RISC type of instructions for using the superscalar functionality. So they convert the CISC instructions into multiple micro ops and then schedule them into execution units, and they get completed. So if you look at the picture, you know all these modules. You know about this, you know about this, you know this, you know pre-decode, you know execution units and reservation sessions. And scheduler means dynamic instruction scheduling. So nothing is there which you don't know inside an Intel processor. That's a good news. You will be able to understand now. Have confidence that you can do it, provided you have followed and have interest to learn. That is very important. I've told you in order here, out of order execution here, Intel also doing the same thing. Whatever theory we talked, you are seeing an implementation by a real processor in the market. Okay, so what you have learned is how important you will know now. So now I am giving you some more details. That is a higher level block diagram. Here some more details. So let me quickly, instruction cache, instructions are pre-decoded when they are read from instruction I cache, and if they are entered into the instruction queue. Some are complex decoding, some are simple decoding. Let me explain a little bit. What is coming in is a CISC instruction. There are many of the CISC instructions can be directly mapped to RISC instruction. That is, in Intel's terms, it is macro ops which are CISC instruction. This is micro ops at the RISC instruction. So macro ops can be directly mapped to micro ops most of the time. So simple decoding is possible. Complex decoding is for some of the specialized instruction, long instructions, which need to be split into multiple micro ops. If you see here in the picture, it shows you 4 micro ops here, whereas there are 1 micro op here. That means 1 macro op, that is 1 CISC instruction, converted into 1 RISC instruction. Whereas 1 CISC instruction getting converted into 4 RISC instructions. Inside Intel, it is called micro ops. If you join Intel, all their document will say micro ops. It is nothing but a RISC instruction. Now, there is one thing which is coming here. Okay, I will not go into the detail now. Don't worry. This is called in order front end. Whatever I explained to you. Now let us come here. After the instructions have been processed, decoded, converted, only Intel doing this conversion. Okay, other ARM and other processors which are RISC outside, means there are RISC instructions for the outside world also. They don't do this job. Remember, this is only Intel specific. Don't assume this is done by every processor. Okay. Now, register aliases is another name for renaming. Alias is what? Nothing but a renaming. Then you have a reorder buffer. 128 entries are there. What I showed you was 8 entry reorder buffer yesterday. You can see in a real chip, 128 entries are there. Huge. Okay? It is all inside one core. I am talking about single core. I am not even talking about quad core. This is repeated 4 times. You can see the complexity of the circuitry inside one single chip. Then we have a 36 entry reservation station scheduled on different functional units. You can see them. There are some ALU with shift operations, floating point operation, adder, multiplier, divider, and SSC. I told you SIMD is here, and all the load store is separated out so that they can write into memory, data cache. They are all here grouped together. Okay, I want you to spend some time, understand it. And one most important thing, hyperthreading, where is it shown? I want you to identify the block in this diagram which is showing the hyperthreading. That is multiple context maintained by the CPU. I told you Nehalem chip Core i7 supports 2 threads inside each core. And I told each core needs to have a separate register set, separate interrupt logic, separate stack pointer, program counter, whatnot. This register set, in our case, in Core i7, includes all MME, SSC, MMX, SSC, floating point register set, integer registers, everything put together. All of them, what you saw, the first diagram, 64-bit, 128-bit, all nonsense. Everything is replicated twice. Where is it? here. There are two things shown which are program visible state. So if a particular thread gets context switched, only this content will be saved. None of this will be saved. But let me explain now hyperthreading on this diagram. So what is happening? I showed you some picture, red color, yellow color instructions coming in, correct? And then getting executed by multiple functional units. You can imagine the same thing happening here. You are getting the instructions belonging to two threads, not many threads, two threads. Who decides it? OS decides it, and they feed the instructions into the CPU. So two streams of instructions belonging to different processes are coming in, or different threads are coming in. They are getting decoded. They are common unit up to this point. Everything is common. So those instructions, one set of instructions will be operating on this register set, another set of instructions will be operating on another register set. Their operands are different. Though it will say R1, either it is maybe here or maybe here. We don't know. It depends on to which process or a thread that particular instruction belong. Similarly, to this register set is also mapped. As far as the functional units are concerned, they don't care whether that instruction belongs to thread 1 or thread X or thread Y. They execute one instruction, maybe belonging to this thread or maybe belonging to this thread. And more, you have seen that they are not accessing the instructions also, register set also directly. They are going through the reorder buffer, right? Reorder buffer only is accessing the register set. You can see them, they are accessing it. So as far as functional units are concerned, they are given some operands values and then asked to do a multiplication job or a division job. It will do. It doesn't care whether it is doing it for which thread, and it will write back into ROB in a particular location. Now ROB, there will be some entry to identify whether it is supposed to write the result into this register set or this register set, and they will keep clearing them. It depends on how it is implemented inside, and I don't know the details. So it is maintaining two different entries for each thread. It makes sense to maintain two different entries because instructions belonging to one thread is one sequence, another sequence should be another thread. You cannot mix them both because you have to keep flushing the instructions belonging to one thread and another thread separately. They cannot, you cannot say that they are interlinked, then you are mixing them. So it will be maintained separately. Whether each of them are having 120 entry or they share 64, most probably I feel it will be 64. Okay. That means each thread is having the set of instructions in them and they get scheduled into the register set, written into the register set in the order in which they came in. So I hope you can understand how two threads, in our case only two threads, are executed simultaneously. That means you are getting two streams of instruction belonging to different processes. They have different register set. They come inside, they get decoded, they get converted to micro ops, all that. Then they get scheduled on the functional units, and they get executed by the functional units, return into the ROB, reorder buffer, and reorder buffer flushes those results into the register set. So this is a sequence. Now, how does it help? First of all, why are we doing it? I told you, to keep the functional units busy. So suppose if I don't have an instruction from one stream which is performing an SSC multiplier job, and I have the same instruction in another thread, I can schedule it here. So let me tell something more. The efficiency that you gain, or the amount of time you get gained by running those instructions on multiple functional units is dependent on the application, what type of instructions you are getting in. Based on that, the parallelism can be better. Okay. Beyond that, I don't want to spend. I think we are running out of time. So I already explained it. This I will not do it. You read it if you want it. Learn. Okay. So I am not going to explain this. Already you have seen them. I have given it for clarity. Understand them. Okay. This is the out of order. Two blocks I showed you. I'm just expanding it here. That's all. Nothing much. Okay. A very architected state is shown here. So guys, in order is for the front end, out of order is for execution, and in order for retirement. This has been told hundreds of times, so I don't need to explain it. With this, we are going to break. What is the time? I don't know. Okay. I will take not more than 20 minutes. Two things I want to teach you. Very, very high level, not going into the details. 1 second, my feedback is high. Okay. What is branch prediction? You know, it is something to do with the branch instruction. So let me give a overview before I go into the details, so that you understand the context. We have set of instructions, and I told you that basic block is something which does not have any branch instruction. Basic block is set of instructions which are either load, store, or data arithmetic or logical, whatever, floating point operations. Load, store is also part of it. But there are no instructions in the basic block which can change the flow of the program. When I say change the flow of the program, none of those instructions change the PC value, program counter value. If an instruction on execution changes the PC, that means it is not going to follow the sequence, because normally PC will be incremented and it keep on going, and it will get modified only when the following instructions are there: either unconditional branch, that means it wants to jump to some location, or conditional branch, based on some flag or combination of flag values, it decides to either go somewhere, go to some other location in the code memory, or continue. We say a branch taken when the PC value changed to something other than incremented value. Okay, maybe one more thing I should tell you. I told you that some instruction changing the PC value. That doesn't mean that during the basic block execution, PC value is not changing. It is changing. If the PC is not changing, it will be executing the same instruction again and again. It is changing, but it is not based on the execution result of an instruction. It is dependent on the size of the instruction. In a RISC processor, all the instructions are of 32 bits wide, so it will be incremented by +4. If it is a RISC processor, you are not guaranteed to have all the instructions of same size. You may have a 4-byte instruction, maybe another 8-byte instruction. Then PC value, it will be, actually what happens normally in a processor is, when it is fetching the instruction, it doesn't know anything about the instruction. Pre-decoding is done little bit during the instruction fetch itself, but incrementing is like a based on the width of the memory. In fact, in real life, what happens is, suppose your CPU is connected to the, in our case, it is always connected to instruction cache. So it will be either 128-bit or maybe 64-bit. It depends on the width of the data width of that bus. Instruction is coming into the data bus, but it's actually instructions which are coming in. So it will be keep incrementing and fetching the instruction one after the other in the increasing address. Please remember, it is increasing address always. Stack only can go backward, forward, and all that. But always PC keeps on increasing, keeps on going on accessing the instructions in the higher address than the current address. Now, jump instructions may come in between because of for loop, while loop, call function, or whatever. So they will change the PC forcibly to fetch some instructions which are in some other part of the memory, instruction memory. So I told you conditional branch, unconditional branch here, conditional branch here. Based on the condition, it may go to some other location to access the memory instructions, or it may continue with what it was doing. Next, call. Call is a subroutine function call at the assembly level, similar to function call in your C program. The only difference between a call and a jump is once the jump happens or a conditional branch happens, there is no requirement or a need to come back and execute the next instruction. Default, it will not come. Whereas if it is a call routine, subroutine call, it will go to some other location, execute some set of instruction, and when the function ends, the compiler would have put a return instruction there. Once it executes the return instruction, it knows where to come back. It will come back to the address next to the call function, call instruction, and starts fetching the instruction from here. So as far as the control flow change goes, call routine also changes the flow of instruction. Similarly, a return instruction also changes the flow of instruction. If return was not there, it would have fetched the instructions which are after this return. It is some other memory address. But return makes sure that it has to go back. Now, how will it know the address to which it is supposed to go? If you remember ARM, we said link register. So when the processor is executing the call instruction, it knows that it is supposed to come back when return instruction is executed later sometime. So it stores the address, next instruction address in the link register as a part of execution of call. It is a responsibility of call function, call instruction to take care of it. So the processor will do it. It will keep default store the PC plus 4 to link register or 13, I think. Then when return instruction is executed, its job is to look at R13 value, put it in PC, load it in PC. That's all. It will come back. So these are the routines which are disturbing the flow. And one more thing before I start, go to the next one. An interrupt. Interrupt can come from the external world, and the interrupt controller will tell the CPU, start doing whatever you are doing, go to the ISR routine, which is in a fixed location somewhere in the ISR table. That also changes the flow. That means PC is loaded with the interrupt table address. Okay. Or let me explain to you in Intel what happens. In Intel, actual PC value is stored in a fixed location in the interrupt vector table. Based on the type of interrupt has come, suppose interrupt number 2 has come, it will go to a fixed location in the memory, data memory, okay, where the PC value is stored, where it is supposed to go. In Intel, there is a segment register that is also stored. Don't worry, it will pick the new PC value and puts it. So these are the instructions which are changing the flow, that is changing the PC value. Now, why are we talking about this now so much? Because we are implementing the processor in a pipeline. We have too many instructions in the pipeline. In a superscalar, we have functional units, and then they have so many instructions in the super functional unit. Now, one instruction, which is a jump instruction, comes in and says, enough of executing this, guys. I want to go somewhere. I want you to execute now. After this jump, go to this address, start picking up instructions from there. Now, what happens to those instructions which are already there? Let me explain. Once the jump instruction is executed, whatever the instructions which are in the pipeline in different stages of execution could be the ones which are to be executed after jump. We are always fetching the instruction ahead of time, start executing them in the pipeline so that we get the parallelism. But suddenly one jump came in, and when I executed it, because similarly there are so many instructions getting executed, so I need to now stop doing whatever I was doing after jump. This, whatever is supposed to be done before, I should complete it. I am not saying that it should not be, it should be. Then I should flush these instructions out and start fetching from the new address all the new instructions which are there in that place. So pipeline will be flushed, all the function units will be flushed, ROB will be flushed, reservation station will be flushed, everything is fresh, new. We are starting from scratch when we change the flow of the program. Either it may be because of interrupt, it could be because of exception, it could be because of a call function routine, or it could be because of return instruction, control jump, unconditional jump, doesn't matter. If I am changing the flow of instruction, PC is loaded with a new address, I am going to fetch new set of instructions starting from that address. That means pipeline, whatever was there, needs to be gone. They need to be completed properly so that I complete all the instructions and write back the result into the register set, which are there in different stages of execution, and then jump. So that is what will normally be happening. Okay. So now what is the impact? I am saying that if I have to jump, I have to flush everything. Then what is the advantage of I am having so many function units, I am parallelly executing them, and then you are telling me that very often you just flush the pipeline. It's a stupid thing to do. Now, is it possible that I can do something? So suppose if I have a set of instruction and then there is a jump, conditional jump on 0 to something. Now imagine a situation where you have a for loop. For loop means jump on not 0, not equal to 0. Okay. For loop, what happens is you normally say if I is less than 0, if it is true, or I is less than 10. If it is for loop is for 10 times, you will say less than 10. You go back to the location for loop. Inside that for loop, there are some set of instructions. You keep going back 10 times. Okay. It is actually a conditional jump. At the end of for loop, there is a conditional jump telling the processor to go back to the start of the functional unit. So it will be fetching the same instructions again, but it is starting from the front. Okay. Number of instructions in the for loop depends on how big your size, for loop size is. If it is only single instruction, you may be executing not single, maybe some set of 5-6 instruction, you will be executing them again and again. So what is the probability of jumping back compared to coming down? It is now 1 by 10. Suppose I have a loop for 1000. 1000 times I will be going back, and at the end of the for loop, I will come out and then come in below and execute the instruction. So majority of the time, almost 1 by 1000 probability that I am going, sorry, 1 by 1000, 1 by 1000 probability I am going to come down, and majority of the probability, majority of the time I am going to go back. For loop I am going to 999 time or 1000 times I am going to go back, and only once in 1000 I am going to come down. So the probability is higher for going back than coming down. If suppose I have a logic in the processor to predict it, and when I see a JC, I start, because I will know by decode stage itself, I will know that this is a jump on jump instruction and conditional jump instruction, I will know within the decode. In fact, in a pre-decode is there, while fetching itself, I will know, hey, this instruction is a jump instruction. If not, that processor doesn't know, it knows. Then what it can do, if it has the address of some other structure I have maintained the hardware, if I have the address of this instruction, I can load the PC with that value even before I execute this conditional instruction, because I know that I have a higher probability that I will go back. So the branch prediction logic in the processor does this. It predicts whether it is going to go down, whether it is going to fetch this instruction, or it is going to fetch some other instruction and then start from there. Now, as soon as I fetch the GSE, I will not increment PC blindly and go forward and execute, fetching the instruction. I will immediately change the PC value. Hey, this is the new value, start fetching from there. But am I guaranteed that this is going to happen? No. There is a probability 1 by 1000 that I am going to discard this flow. I'm going to start from this address. But majority of time I'm going to be predicting it correctly. So whatever instructions which are there in the pipeline are the ones which are supposed to be there. There is no need of flushing the pipeline. So I have predicted the jump correctly majority of the time. So I won't be flushing the pipeline. I won't be stopping any execution in the execution unit. I will continue as if nothing happened. This is the job of branch prediction. Okay, how it is done, I'm not going to show you. So branch prediction is a logic which is active from here onwards as soon as the instruction comes, and then it will think, okay, what do I do? Should I change the PC to what? Should I increment it or put a new value there so that I go to the target? I do it there. I take care of it there. During the recode decay, the rename case also, some inputs are going because some new instructions are coming in. I will be handling it. Then when I commit, that means when I am finally sure whether my jump on carry or whatever instruction I have thought that I am going to do is correct or not, I will come to know. Whether my prediction is true or false, I will come to know when that particular instruction gets committed or executed. Committed means it's the final stage, right? So why am I waiting till commit? Remember this. It has to wait till commit because jump on carry is here. There are so many instructions above them. And then from jump on carry, it is going to take some new instructions. Now all these instructions have to be completed. That is going to happen from the ROB. Okay, from the ROB, committing is happening. It will commit JC only after committing all of them. So I will come to know whether I am JC is what decision it has taken. Then I will update it here. So this is another method of implementing branch prediction where based on the previous prediction, I adjust my thinking. If previous prediction said it was going to the back, whether forward address or backward address, based on which decision was taken, I will know whether next time can I predict it closer to what has happened previously. So there are some logic built into the branch prediction to predict the jump most with a higher probability. So I need to know the decision finally what was taken. Suppose my prediction was wrong. It was not true. Whatever I thought, and then I fetched instruction which are all coming inside, already come inside. My prediction is wrong. What should I do? This is what you have to do. If suppose my prediction is wrong, kill all the instructions which have come and I executed them with the hope that my prediction was correct. Now everything went for a task. My prediction is wrong. I cannot say that no, I predicted I will do whatever I thought. No. Now it says that you are not, what you predicted is wrong. You have to fetch a new set of instruction. That means whatever you did earlier based on the prediction has to be killed. In the sense, it should be made null and void. No register state should be affected. Only thing is, some instructions have been executed somewhere, some maybe in the halfway through, remove all of them. If already functional unit is busy doing some division operation, which is to be removed, just tell the functional unit, stop doing division. You will not, I don't want to wait for 40 cycle. You stop doing the division. Enough of it. Come out. So you can interrupt any of the functional units to just stop doing what it was doing and start feeding the new instructions there. That's all. So based on the prediction, you start executing instructions ahead of time. That is called speculative execution. I am covering what is coming next. Speculative execution is some set of instructions are executed hoping that the program control will come there. Okay, so branch prediction is one. It predicted it that it will go there and started executing those instructions. So it's called speculative execution. But those speculative executions are still in the execution stage, or maybe they will be in the ROB, reorder buffer, but they are not committed yet onto register set. That means you are still on the safer side. Even though you have executed those instructions, even though you have completed them, even though you have found the results of those instructions which are available in reorder buffer, they won't be committed to register set. As long as I don't commit to the register set, I can afford to do anything. This is similar to that most of you do in the exam. If you are, I have seen all of your papers, there will be a one page. You will write all kinds of equations, all kinds of driving out, trying out something. And then finally, once you are sure that that is the answer, you come and write it in the answer sheet. I never catch you on those rough work and then say, oh, your mark is wrong. No, I will not give you mark because you found your answer is wrong in that particular rough page. No, rough page is rough page. This speculative execution is similar to what you do in preparation for a final answer. But what your value, what your marks are given, how they are given is based on final result that you have put in. Similarly, those instructions though executed by the processor, they are ignored. They are killed if the prediction is wrong. If it is correct, they come to the actual answer. So if suppose you try out something and then you say, you think that what you thought is wrong, what you do, you stop there, and then if there is a option that you can pick another question, you do that. So rough work is to make sure that what you are doing is correct. If you are convinced that it is correct, you come and make a fair copy. Same thing processor does. It will do all that predictive speculative execution, but if it is correct, it will be taken. It's not that always it is discarded. If it is wrong, prediction was wrong, and the processor was supposed to go somewhere else, it will go blindly there and forget about what it has done so far. So this is in a nutshell what is a branch, branch prediction or resolution after actual result is found. So one slide. Processor may speculatively start fetching and executing instruction from a code path before the outcome of conditional branch is determined. It doesn't know what it is doing is wrong or correct. It starts doing it, hoping that it will be correct. If it is correct, copying is easier. Your rough work is paid you just copy that result, you are done. But if it is wrong, you have wasted some time, but it's okay. As far as the CPU is concerned, it was doing something constructively during that time, because anyway functional unit was going waste, it was executing it. If it is a waste, nothing can be done. It will come and start doing the proper work. So branch prediction is commonly used to predict the outcome and the target of a branch instruction. it goes to the target address and starts fetching instructions from there. However, when the path is determined not to be the correct one, the processor has to cancel all the intermediate results and start fetching instructions from the right path. Nehalem, as other modern processors, invest heavily into prefetching for speculative execution from a predicted path and translating them into micro-ops as possible. So it is actually prefetches the instruction on the predicted path and start executing, processing, decoding, all that it does with the hope that it is going to be right. A dynamic scheduler then attempts to maximize the number of concurrent micro-ops which can be in progress at a time, thus increasing the completion instruction rate. Let me explain why we are doing it. You may think that, okay, if you are going to scrap everything, then don't do it. Just wait till the control instruction result is out. Then I will worry about what to execute, what to access. It is like not studying before the exam. Let the exam come. I will read one day before it. Then you encounter that there are too many things to study. You need to watch the video, which is not possible. This guy has spoken for hours. You will encounter that kind of problem if you do not use your functional unit, which is the brain, consistently. If you do, during the final exam time, you don't need to spend too much time. You can still spend time on Facebook. Processor does the same thing. It doesn't want to keep the functional unit free. It wants to occupy with constructive work. Instead of doing nothing, it is predicting that these are the set of instructions likely to come. It starts executing it. If the prediction is correct, it is going to benefit. Already the job is done. It can keep producing results. So that's the advantage of doing the branch prediction and doing a speculative execution. So I have already spoken about it. When I spoke about branch prediction, I have covered this also. So let me just tell you. This is a one state. This is one if condition. It branches onto true or false. And inside that you have another if condition which is going to branch or false. So there are so many like this. You might have written the code in your program. So if the instructions are executed on the basis of predicted branches, suppose I predicted like this, it is true and this is going to be false. So what I do, let me explain to you. The instruction which is in this case, this is one jump instruction in a particular address, and there is another jump instruction, jump, conditional jump, which is in some different address. So I maintain the previous result of these instructions in a table, branch target buffer. And what was the result earlier? So if I have a for loop, inside the for loop, I have so many if else. Now, each of those if else conditions have some conditions which you have tested it on one iteration. Then you are going to come back in for loop and then going to execute the same thing. If I remember these decisions of if else then else, when I come next time, I will know what was the decision I took earlier. Most likely that will be the decision now also. So I predict it based on that. That is called branch target buffers, maintaining the decisions taken on each of those branches. So multiple entries are maintained and it maintains the previous result. And if you execute the same piece of code again, you will come across the same instruction. Now you will see the table and see, hey, last time I predicted it to be true. Maybe this time also it will be true. So let me start fetching instructions from the true path where it is supposed to go to if it is true. If I am successful, fine. So if your for loop is such that on every iteration, the if else conditions are going to be same on every iteration, your program will run much faster. So there are some techniques to optimize your code so that this kind of branch prediction behaves as you expect. Okay. You can actually, if you have this idea, when you write a code, you can think about it and write it in a better way. So it does a speculative execution. In such cases, ROB needs to be cleared. If suppose your prediction was wrong, ROB needs to be cleared wholly or partly. Remember, wholly or partly. It has to be cleared partly, because if jump instruction is here and then you predicted it wrong, this set of instruction, but the instruction in the ROB, I am showing you ROB, this instruction before jump has to be executed. They need to be committed. So you cannot say I'll destroy whole ROB. No. If JC is there in the middle and then there are some instructions above which should have been executed before coming to JC, because it's a superscalar. So you have to commit them and then stop. You don't have to commit these instructions only. I hope these are all clear to you. If there was a misprediction, if the prediction turns out to be correct, the entire ROB can be committed. No issues. Okay. All that what you have done is valid. So you can just query on. So the performance benefit of branch prediction can only be gained if prediction is followed by speculative execution. So what is the use of prediction if you don't do this? Let me give an example. Suppose during the class, based on the stress that I am doing on some particular topic, you predict that more questions are likely to come from scoreboarding or dynamic instruction execution. You predict it correctly, but you do not do a speculative execution. What does it mean? You do not go and read about that. What is the advantage of predicting it correctly? Maybe in the exam say, oh, I thought this questions will come from this. If I have read this, I might have done well. I might have got good marks. I might have got good grades. Everything would have become might. But if you have done speculative execution of reading up this topic which you predicted is going to come in the exam, you are going to gain from it. So processor cannot just stop predicting it. It should do speculative execution also. So it will do it. That is what is, that's why both of them are together. So to support deeper and wider multiple issue instruction pipeline, what I mean by deeper, number of stages are more. Wider, I have a wide number of functional units, I can issue more instruction. Then if I need to keep the instruction flowing, more instruction keep flowing into the pipeline, I need to do a prediction. I need to do a speculative execution. Both need to be done so that my job that is I am doing in a pipeline is not wasted. All the instructions that I've brought, they're all valid instructions and I am gaining from it. So forthcoming means the instructions which are coming after the branch instruction. Forthcoming instructions have to be fetched correctly. If you have predicted it correctly, you would have fetched the correct instructions and you would have executed them and you will gain from it because you don't have to flush the pipeline. So instruction window, that is amount of instructions that you are fetching from the memory, number of instructions is called instruction window. It can be wider if you have a wide instruction queue and all that. Okay. So integration of different techniques. This is the last slide, Mobi. If you want to improve the performance of a processor, you need to have this. You need to have this. What is the reason? You need to have this so that you keep speculative execution done in a right direction. Why should you do this? So that you have a functional units which are busy always. You keep issuing multiple instructions to them. Why do you do this? Because based on the correct prediction, if I start executing the instruction, I don't have to flush the pipeline. Then on branch also, I don't need to worry about it. One more point I will tell you, the percentage of jump coming in your code is much higher. Okay. If you see your code, control code, there will be so many if conditions, switch statement, for loop, function calls, so many are there. So they are more frequent. That means the number of instructions that you can find in a basic block is coming down. If basic block is smaller and smaller, you don't have sufficient instruction to keep your pipeline busy. You have to do speculative execution and branch prediction to keep your pipeline busy with many instructions. So you cannot avoid it. Internal data paths, how you pass on the register renaming values, renamed register values in the resource stations, reservation stations. That is the internal data path. Many functional units. You need to have many functional units so that parallelism can be better. So, and you have to keep the instruction queue more wider, and the bus connecting the instruction memory also wider, so you get more instructions from the instruction cache, and you do a decoding and all that. So actually you have understood all of them. I have explained, or you are supposed to have understood all of them. If you have followed me and taken interest in the lecture, not on Facebook during the class time or on the messenger, you might have really gained from these lectures. I have put in my effort. I don't know how much of that is going to be useful. I still have my own doubts, but I have done my duty. It is your responsibility to either use it or throw it. So with this, I am not going to cover about this one. You are supposed to do a self-study. I will mention it in the slide. This is for self-study. So we are coming to the end of this lecture. We have one more. I plan to do multi-core processors and cache coherence tomorrow. With that, I have completed 100% of what I wanted to cover. Okay.